Assalamualaikum warahmatullahi wabarakatuh. Welcome back to our second part of this thermal management chapter. In the first part, I already explained to you about the thermal characteristic and thermal basic on the electronics circuit. Okay, so in this second part, we are going to focus on zooming into the detail of the power dissipation and temperature characteristic for Mosfet and also the Schottky diode. Okay, in this second part, I will explain about that, and then we have the third part, which is the example or the exercise on how we can design the thermal heatsink for the converter. Okay, the first one we start with the thermal management for Mosfet itself. Okay, so before we proceed with the Mosfet, I think it's better for us to refresh back on the analogy, okay, between the electrical and thermal. Okay, and then here we have a diagram of electronics component. Okay, and then we have the heatsink here, the yellow one. This is the heatsink. I think this is common for the one who usually like to set up their own PCs. They will know what is heatsink. Okay, but this is generally a common one. Okay, you can find this heatsink inside any electronic devices. Okay, so there are several points within this that you have to know. The first one is the junction temperature, indicated by the TJ. So TJ indicates the junction temperature, and then we have TC. This is the case temperature, the temperature at the case here. Okay, and then we have the TS, which is the temperature at the heatsink. Okay, at the surface of the heatsink connecting to the device. And then finally we have the ambient temperature. Okay, this is the room temperature that device are located in. Okay, and then we have the RTH. Okay, this is the thermal resistance. If the thermal resistance here indicates J and C, so this is the thermal resistance between the junction and the case. Okay, from here to here. Okay, and then the equation is the delta T, which is the temperature difference, divided by the P, the power dissipated. Okay, so in this case we have Tj minus Tc. Okay, if the RTH J to C mean the Tj minus Tc divided by the power dissipated. Okay, so this is how you define the thermal resistance between the junction and the case. Okay, basically between the junction and the ambient, okay, the temperature junction and temperature ambient, we have several RTH. The first one is RTH J to C, junction to case, indicate by RTH J to C. And then the second one is RTH C to S, and then the final one RTH S to A. C is case, S is the heatsink. Okay, and then this one is from heatsink to the ambient temperature. Okay, this is the internal construction for a Mosfet. You can see a series of resistance here. Okay, these collectively they are called the RDS, the resistance from drain to source. And the RDS on mean that the amount of resistance we can measure or we can have from the drain to source during the switch on time. Okay, and when the MOSFET is turned on. Okay, here we have the VBR-DSS. This is the drain source breaking voltage. So this is the minimum voltage the device is guaranteed to block between the drain and source terminal. Okay, during the off state. So in other words, you can say that this is the rating of the Mosfet. So here we can see the graph between the rating of the Mosfet or the breaking voltage versus the normalized RDS on. So we can see that when the rating is increased, the RDS on also increase. So we are interested to see on the trend here. Okay, remember when the breaking voltage level is increased, the RDS on is increased as well. Okay, secondly, we want to look at the ID. This is the drain current. Okay, you can see that when we have the drain current at lower here, let's say for 10 volt. Okay, the 10 volt here is the VGS. Okay, at higher VGS, you can see that the drain the increase in drain current will not affect or have a small impact on the RDS on. You can see that the RDS on is not increased. But at lower VGS, okay, at lower the VGS, the gate to source voltage, the one that we give to the Mosfet to turn on and turn off the Mosfet. Okay, at the lower value of VGS, you can see that there are some effect lah. You can see at here after certain value, when the current is increased, the RDS on shoot sharply lah. Okay, and then finally we have the VGS, the voltage gate to source voltage versus the RDS on. So like I mentioned before, at lower VGS, okay, we have the very high value of RDS on, but when the VGS increase, the RDS on become small and suddenly will maintain here. So they are also different, okay, when we operate at junction temperature of 25 degrees C and when we operate at junction temperature of 125 degrees C. So the temperature also, the temperature of the device or the junction temperature will also affect, okay, the RDS on. So from the graph here, okay, that we already see in the previous slide, the higher the voltage rated of the Mosfet, I mean this the breakdown voltage, the higher the breakdown voltage, we have the larger RDS on. The RDS on will increase, and this will contribute to the larger conduction loss. So you know when the RDS is increased, we have the I square R losses. Okay, so when the R component is higher, so the losses will also be higher. Okay, and then when we have higher VGS drive, the drive voltage of the Mosfet, the lower RDS on we have. Okay, finally for the drain current versus the RDS on, so we can conclude that for the high VGS voltage here, you can see the 4 here, the RDS on is tend to be independent of IDS. Okay, so when the increase in current, okay, the effect of increasing in current will not affect so much on the increase of the RDS. Okay, from this graph, we also know that the RDS on will increase with the temperature. So the higher the temperature, the higher the value of RDS on. Okay, when the RDS on value increase, so it will contribute to the larger power conduction loss. Okay, higher value of resistance, it means the higher value of I square R losses. Okay, now I want to explain to you about the RDS on normalized value. Okay, so sometime when you open the datasheet, you will find it's, the value of normalized. So what you mean by normalized is this value of the RDS is constructed based on the value of the RDS at 25 degrees C, the value of RDS at 25 degrees C. So that's why you see at this 25 degree you see the value of 1. Okay, so any increment in terms of the RDS after that is relative, okay, to the value of RDS at 25 degrees C. So let's say when you find the data sheet of any component and you see this graph, okay, the drain to source on resistance normalized value. So when you want to know, let's say at 60 degrees C, okay, you want to know the temperature, the value of RDS on at 60 degrees C. So what you have to do is you have to find this value. Okay, let's say in this case is around 1.3 here. You can say that this is 1.3. Okay, multiply by the RDS at 25 degrees C. Okay, so then you will get the value of RDS on at 60 degrees C. Okay, for a Mosfet, okay, the power dissipation or power dissipated from the Mosfet is due to these three components. Okay, the first one is the on state loss, which is the I square R. Okay, that's why I mentioned that the higher the value of RDS, the higher the value of losses. Okay, this is the on state loss. Another one is the switching losses. Okay, the switching loss is due to the switching action on and off, and this is the function of the frequency. The higher the frequency, the higher the switching loss. And then finally they have some internal diode inside the Mosfet itself. So this one will contribute some amount of dissipated power in the Mosfet. Okay, for the power dissipated in the Mosfet, most or the majority of the component come from the on state loss. Okay, so if we see zoom on the on state loss, this is the temperature versus the power dissipation. So we can see that when the temperature is increased, the power dissipation also increase. Okay, so the on state loss is contributed by the I square R losses. Okay, and then this is the function of the temperature as well lah. Because when the temperature increase, remember that the RDS on will also increase. Okay, now we reach the term thermal runway. Okay, so what is thermal runway? So it refers to a situation where an increase in temperature will result to some changes or some condition changes inside the component, and the changes will further increase the temperature. Okay, so it's like domino effect. Okay, when you do something and you cannot stop it, okay, there are some after effect. So this often leading to a disruptive result if it is not controlled properly. Okay, now we will look at how the Mosfet thermal runway happen. Okay, as we know that the junction temperature is a function of the power dissipation. Okay, so the higher the power dissipated, and the higher the junction temperature. Okay, and then the higher the power dissipation also, it means that the higher value of RDS on. Okay, so when we have higher value of RDS on, it will contribute to the higher junction temperature. Okay, and then this cycle will repeat itself. So if we're not controlling the junction temperature at the proper temperature, it can cause the thermal runaway. So in other words, okay, the higher the junction temperature, we will have the higher RDS on. Okay, when we have the higher RDS on, due to the I square R losses, we will increase the power dissipated from the Mosfet. And this one, when the power dissipation become higher, okay, it will make the junction temperature become higher. So this is the transcendental cycle. Okay, cycle that make it worse every time, and then this will cause the thermal runaway. Okay, when we have the transcendental cycle, like we see in the previous slide, this will produce a non-linear characteristic. Okay, and then in Mosfet itself, the on-state losses, which is the RDS on, is the problem due to the non-linear RDS on versus temperature characteristic. Okay, so for the Mosfet, the problem that can cause the thermal runaway is the increase of RDS on based on the temperature. So normally when they want to solve the transcendental process or equation, it require the iterative process. So what I mean by iterative is the repetitive process to find the value of junction temperature and then find check whether the operation is okay or not. So we'll see about this process in the next slide. Okay, this is what people normally do when they want to design the operating point for a Mosfet. Okay, first they will assume the junction temperature of the Mosfet and make sure this is lower than the maximum junction temperature. And then based on the junction temperature that they selected, they will find the value of RDS on, okay, in the data sheet. Okay, based on the RDS on, they will calculate the power dissipated, okay, at that junction temperature. Okay, after that they will select the ambient temperature of uh, the location where the device will be put, and then from that they will determine the RTH junction to ambience from the data sheet. Okay, so after they find the RTH, they can calculate the delta temperature junction to ambient. So this is the temperature difference between the junction and the ambient. Then based on that, they can calculate the junction temperature. They want to find the junction because they already know the ambient temperature. They want to find the junction. So after that, we need to check, okay, whether the junction temperature that we get is higher than the junction temperature that we assume. If yes, if this one is higher, then we have to reselect, or we have to select other value of junction temperature and then repeat this cycle again. If the value is lower, okay, we have to check whether it means that the junction temperature is lower than the uh, the one that we set here, then it's okay. Okay, so we want to avoid doing this cycle. Okay, this is, let's say we select a wrong value, then we have to do it again, to find this one value, I mean this condition that have our junction temperature to be lower than the one that we select just now. So our target now is to avoid this iteration process. Okay, we don't want to let's say try and error, I mean try one value and then calculate. Okay, there are some other method that can avoid this iteration. Okay, now we are moving to the second device that you are interested in, which is the Schottky rectifier or Schottky diode. Okay, so this is a diode that have some special characteristic, which is low forward voltage drop and very fast switching action. Okay, so it have these two characteristic for low forward voltage drop and very fast switching capability. So we want to look at the thermal characteristic for these devices. Okay, these are the parameters that are common for Schottky rectifier. The first one is the forward voltage drop or VF. Then we have the junction temperature, the maximum junction temperature, the forward current, reverse voltage, and reverse leakage current. Okay, this figure shows the internal construction of the Schottky rectifier, but we are not going to go into the detail of each of these components. We are more interested to see the thermal characteristic for the Schottky rectifier. So the first one that we want to see is the forward voltage versus temperature. So this is the polynomial relation, okay, using this equation. Okay, but we know that when the temperature increase, the forward voltage decrease. Okay, and this is the relation between the forward current versus the forward voltage. And then you can see here when the temperature, okay, increase from here 25, 125 and 175, we can see the reduction in forward voltage. So this is relate to this graph, okay, in terms of the trend. Okay, we can say that for Schottky rectifier, the forward voltage will reduce when the junction temperature increase. Okay, and then this conclude that the on-state losses will cause no problem to the operation of Schottky rectifier, as long as the junction temperature that we are operated on is lesser than the junction temperature maximum. Okay, so as long as the device itself is operated below the maximum junction temperature, it should be okay. Okay, now we are looking at the Schottky diode power dissipation during the on stage. Okay, so during the on stage, this curve of the Schottky rectifier power dissipation will follow this one. It will follow the forward voltage shape. Okay, the curve like this. So that's why you can say the same shape for this. Okay, because the power during the conduction period or during on period is equal to the VF multiplied by I average. So you know that when the temperature increase, the voltage decrease. So this will contribute the reduction in power power dissipation. Okay, now we are going to see the next parameters for Schottky rectifier, which is the reverse current. So the relation between the reverse current and the junction temperature is when junction temperature increase, the reverse current increase exponentially. Okay, so that's why we can see here uh, the curve went exponentially like this. Okay, and then when you relate the reverse current and the reverse voltage, I mean that when the reverse voltage increase, the reverse current also increase. Okay, so here when we have the Schottky rectifier power dissipation during the diode switch off, okay, we can see that this is the trend, and the curve will follow the shape of reverse current versus the junction temperature. Okay, why it follow the shape of this? Because for the power dissipation during the switch off is equals to V reverse multiplied by I reverse average. So when you know that when I reverse or reverse current increase, so the power dissipation will increase as well. Okay, so it will follow the shape of IR versus T junction. So for the total power dissipation, we have to combine both graph that we already seen. First one is the power dissipation during the switch on time, and the power dissipation during switch off time. So we can see that this area is pretty dominant by the on state characteristic. Okay, and then this here follow the I reverse characteristic. So at this region, this is the possible thermal runway region. Okay, the thermal runway for the rectifier, the relation is, we know that the junction temperature is the function of the reverse current, and then when the reverse current increase, okay, this will increase the power dissipation, okay, the reverse power dissipation, and when this one increase, it will further increase the junction temperature. Okay, or in other words, when junction temperature increase, we can see that I reverse will increase, and then when I reverse increase, we have the V reverse multiplied by I reverse. Okay, this is the power dissipated. So when this one increase, this one will also increase. Okay, and when this one increase, it will further increase the junction temperature. Okay, so this will cause the thermal runway. So same with the Mosfet, the Schottky diode also exhibit the non-linear characteristic, but for Schottky diode, okay, it is due to the reverse leakage current. Okay, so it has an exponentially rising characteristic that will create the problem. Okay, now if we assume that the ambient temperature is equal to 40, okay, and we want to determine the thermal stability boundary, we can connect this temperature or this point to this curve here, connecting at only one point of this. Okay, and then at this point, it is called the junction temperature boundary. Okay, if you operate your device junction temperature more than this point, so it is within the thermal instability region, but if you operate it at this point, it should be okay. So in this point, this is junction temperature is less than the boundary temperature. Okay, to achieve a thermal stability, or in other words, to avoid thermal runway, so we must have a heat removal capability which is greater than the heat dissipation of the device. Okay, and the operational junction temperature should be lower than the temperature at the tangent from T ambient to the P Schottky curve. The tangent here means the straight line that we draw before. Okay, so the operating point must be lower than this. So the rule of thumb is it should be 20 degrees C lower than the temperature at the boundary here. Let's say the boundary temperature here is 150 degree C. So we must design our component to operate at least 130 degrees C, okay, to ensure that the operation is smooth. Okay, for operation of isolated forward converter, okay, we have two Schottky diode we use here. The first one is D1 and D2, so represented by Schottky 1 conduction loss and Schottky 2 conduction loss. So this is the conduction loss during the switch on, or when the diode is on. Okay, so we know that this is the power dissipation when it's on. This is it is a factor of the duty cycle use. Okay, let's say normally for forward converter we normally use the duty cycle, let's say less than 0.5, let's say 0.4. Okay, let's say we select the duty cycle to be 0.4. So at this point 1 minus 0.4 is 0.6. So during the operation, the Schottky 2 will have longer duty cycle, which is 0.6. So that's why the conduction loss is higher at Schottky 2 compared to the Schottky 1, where the duty cycle is only 0.4. So we have lower conduction losses here. Okay, Schottky rectifier forward loss curve reduced with junction temperature increase due to the reduction in forward voltage drop. Okay, now we move to the second part, which is the reverse loss, the power dissipation during the off time of the diode. We have this power dissipation equation that have the term 1 minus D switch here. Okay, so Schottky rectifier reverse loss curve increase exponentially with junction temperature. So we can have different shape of losses, and this one differ based on the duty cycle and also the amount of the reverse current and reverse voltage inside the diode. Okay, now this is the graph when we combine, okay, both the losses during the on and losses during the off time of the Schottky diode. So when we combine both of them, we will get this shape. This is for Schottky 1, this is for Schottky 1, and this is for Schottky 2. Okay, so Schottky 1 power dissipation start the upward rise at lower temperature. So when we combine both of them, we can see that the one that start the rise here is at this point, okay, which is the Schottky 1. So uh, it has much greater increase with temperature. So when we want to design anything, we have to choose this one as a boundary condition. We cannot draw something like, okay, this one, the curve here, if you continue with the temperature, it will increase at this point, maybe at 240 something. So we cannot afford to have a design something at 240 degree C. So we must choose the one that has a lower lower temperature, at which point it will increase after that. Okay, so this is the, we call it the critical point that we must scatter. So when we cater the critical point, this one should be fine lah. Okay, so when we want to determine the boundary condition, you have to use the Schottky 1 curve here to determine the boundary condition. So this is the graph that we usually have, the power dissipation versus temperature, but this one is for all the component that we have in the isolated forward converter. We have the Mosfet, okay, usually it will look like this, and then we have Schottky 1 and Schottky 2. Okay, so when we combine both forward and reverse losses, okay, remember that during the forward losses, we have a very straight like this, okay, and then when we reach higher temperature, this curve is mostly affected by the reverse losses. That's why you can see that the increment is at the higher temperature here. Okay, as the junction temperature rises and reverse losses start to increase faster than the conduction loss, so then we can see the rising trend here. Okay, so that's what it means. Okay, that's all for the material that we covered during the second part of this thermal management topic. So just to recap back, in this lecture we learned about the characteristic, the power dissipation characteristic for Mosfet and the Schottky diode, and there are two different parameter that affect the power dissipation. Okay, but both of them can exhibit the thermal runway, so we have to know which parameter or which circuit component that can cause the thermal runway in Mosfet and as well as in Schottky diode. Okay, so later on in part 3 we will cover the exercise and on how can we design the heatsink for our circuit, the converter circuit. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.